All right, welcome to the lecture 20. In lecture 20, we'll talk about the internal stability of reinforcing material. The learning objectives of this lecture is to identify the major observations made in fields on failure surface and maximum tensile force in the reinforcing material and the earth pressure coefficient. So we'll talk about what are the differences from the idealized theory and the field observation. And we'll talk about how to compute the factor of safety against the rupture of the tie and the factor of safety against the slippage of the tie. Right. We talked about before about the general failure mode, and the common failure mode are, the first one is the rupture of the reinforcement, aka or is known as tie break, and the second is slippage between the reinforcement and the soil, and also known as tie pull out. And the other failure modes of the internal failure is the failure of the facing element. Like it could rupture and excess deformation. Also, you can experience the excess deformation and the buckling. And the last one is the connection failure between the tie and the face element. So when we check the internal stability of the reinforcement, there are several approaches, and today we'll talk about the original standard analysis and the revised standard analysis. So two procedures will be discussed. And first one is the original standard analysis. And in this analysis, each individual reinforcement level is checked for rupture and slippage. So let's say you have a retaining wall and earth with reinforcement, and then each reinforcing material will be checked, the internal stability of these, all of the reinforced strips for the all the levels. And vertical and horizontal stresses are determined at each reinforcement level, and factor of safety are calculated assuming the ranking state of active pressure. So active plastic equilibrium in the soil. Okay. So if we look at the typical force diagram here, and then we have a surcharge load, and that surcharge load apply the vertical stress V2, vertical force V2, and the weight of the reinforced block applies the V1. And here, as I talked just before, each reinforcing material will be checked, right? So let's say that we are checking this material, which is at the depth of G. Then you calculate the vertical force applied on this strip at this depth, and also the horizontal force applied here. So F1 and F2 will be computed for the given depth of interest. So sigma V, the vertical stress, will be gamma G plus Q, and the sigma H will be K active times sigma V. And if we compute the F1, 1 over 2 times Ka times gamma times C square, and F2 will be Ka times Q, and V1 and V2, as we just talked in the previous classes. And here, these two factors, the F1 and F2, as you see, there are Z, so this will be given for the depth of Z. And according to the Meyerhoff's distribution, we will need to compute the eccentric length E here. So here, when we talk about this block, you have E, which is summation of F1 plus F2, is the capital E, and that generates the moment. And the W pushes down this block. So you have W, which is the vertical force, and the E as a horizontal force, and the M as a rotational drive. So then, using the Meyerhoff distribution, you can determine the E. So, and if you compute the E, then you can compute the stress for the given vertical force. So W is the total vertical force. So if you know the E, then you can estimate the length here. Sorry, the length here. Length. So then you can determine the vertical stress. Okay? From the vertical stress, you can determine the horizontal stress. So for the vertical stress and the horizontal stress calculated according to Meyerhoff distribution, we can identify the factor of safety against the rupture. So if we think about the strip that's connected to a facing element here, and if the facing element has the area of delta H times delta B, the strip element also will have some thickness, and the cross-sectional area that will be B times the T. So here should be in the thickness will be the T. And then for the reinforcement of interest, so this strip, the tension developed is the T equals sigma H times delta H delta B. So this tension is actually applying here to the facing element. So this sigma H will develop over this yellow area. And for a given yield stress sigma S over steel strip of cross-sectional area AS, the tensile force at rupture will be TS, which is AS times sigma S. So this is the force, tensile force that this strip can resist, allowable force. So the factor of safety against the rupture, FSR, will be TS over TD, and which is AS times sigma S over sigma H times delta B. And this factor of safety should be larger than 1.5. Okay, then what about the slippage? So we also need to check the factor of safety against the slippage. And the maximum possible shear stress tau S is developed over the surface area 2BL over strip is tau S times sigma V times tangent delta. So if we go back this, then the slippage will be developed on this face and the bottom face. Right? So that's why we multiply 2 here and times B and L. And E will be here, and L is the length. And here the delta will be the effective skin friction angle between the strip and the soil. The maximum pulling force of strip of length L and width B can resist before slippage is TR was 2BL sigma V tangent delta. So this is the maximum force that the strip can resist before slippage occurs. For the reinforcement of interest, the tension developed before slippage will be the same. TD will be sigma H times delta H times delta B. So this tension will develop by this sigma H the same, right? So the force is pushing this facial facing element. So then the stress will be also developed as a kind of skin friction, or it could be internal tensile stress. So if it's internal tensile stress, that will be a rupture. If the slippage is less, then that will be slippage failure. So the factor of safety against the slippage will be TR over TD, so resisting force over the driving force, and 2BL times sigma V times delta, and sigma H times delta H times delta B. So this will be the driving force, and this is the resisting force. And the factor of safety against the slippage must be greater than 2.0. And that was the original standard analysis, and there are other analysis procedure which is called a revised standard analysis. And this method of analysis takes into account a number of findings from laboratory model tests and field measurement. For example, the first one will be the failure surface are curved rather than straight. So simplest approach for the failure path takes a bilinear form originating at the toe of the wall. And this means this one. So here A, before, when there's no reinforcement, the failure will be linear like this with the 45 plus phi over 2 angle. But with the reinforcement, the failure surface will be curved like this. So in a simplified scheme, you can idealize this failure surface with a bilinear. So one line to the half of the wall height, straight, with the angle of 45 plus phi over 2. And then it becomes a straight to the top, straight vertical to the top. And this is the bilinear failure path that we use in the revised analysis method. Then the second is the maximum tensile force in the reinforcing strip occurs at some distance behind the wall surface, which is approximately 0.3 H, suggests the concept of the effective length. So here, when we talk about the resisting force against the slippage, as the wall moves this direction together, this whole block will move together. So the slippage here, or the frictional force, would not help in resistance. Only the slippage here, or the frictional force, will help in resisting the active pressure. So this is called the effective length. So here the LE will be the effective length, and the tensile stress is not linear or the constant over the length of the strip. So here shows that tensile stress applied over the length of the strip. So you can see that this is the maximum, and that's about 0.3 H. And the other note is that the maximum tensile force, Tm, is 85% of the maximum tensile force will be applied at the connection part, at the wall. And the earth pressure in the high walls, which is over than the higher than 5 meters, vary from K0 near the top of the wall to the Ka to a limiting depth below, and remains constant beyond that point. So this is drawn the sketch it here. So K naught, so at the top, in the reinforced earth, at the top here, the horizontal earth pressure or the lateral earth pressure coefficient is close to K naught, and it becomes Ka decreases with depth, and then it stays constant. And this deflection point is about 6 meters. So if you are interested in this strip, then you use this value, so K naught, and this will be the Ka, and this value to compute the horizontal stress. And if you're interested in here, then you use this Ka to compute the horizontal stress. And the last observation here is the soil strip friction factor F star, which is tangent delta, for the ribbed galvanized steel strips vary from F naught, vary from 1.5 near the top of the wall to the tangent phi 1 at the depth of 6 meters and below. So if it's ribbed steel strip, and this F naught will decrease to a depth of 6 meters to a tangent phi 1, and here this value is 1.5. So smooth strip, then you just use like tangent delta, for example 0.4, regardless of depth. A ribbed strip, so the strip has this kind of a rib. Right. Then the F, the frictional coefficient, friction factor, will vary from 1.5 to tangent phi 1. Or for the preliminary design, you can use this equation, 1.2 plus log Cu at depths of 0 meter, and deeper than 6 meter, you use the tangent phi 1 constant value. Right. So then the typical scenario is given here. For the wall height of H, the L, the length of the reinforcement is generally 0.8 times H, so 80% of the wall height, and Q is the surcharge loading. And if this strip is selected for the analysis, then you can compute the F1 with increasing horizontal stress with depth, and F2, which is caused by the Q, the surcharge load, and the facing material will give you the panel area, and the cross-sectional area also required to compute the tensile stress, the maximum tensile force that strip can resist. So the allowable stress in each strip will be known as Fy, and usually each facing there will be an n number of strips symmetrically placed. So in this example, it has 4. 1, 2, 3, 4. Then now we can think about the real actual computation, the calculation. Analysis for the reinforcement located at depth C. The V1 is caused by the weight of the block, right? The soil block, gamma Z times B. And V2 is the surcharge load, the vertical load by the surcharge as Q times B. And F1 will be 1 over 2 gamma K A2 G square. So this will be the F1 and this will be F2. And E, also we need to compute the E, right? to follow the Mayer-Hoff distribution. Here E is the summation of the moment at depth Z. So that's gonna be this block, and the moment, the pivotal center will be at the center, right? The half of the width, or half of the length L. So E will be V1 plus V2. And to apply the Mayer-Hoff distribution, you can calculate the sigma V, the vertical stress, for the given vertical forces. And then you can calculate the horizontal, the lateral earth pressure coefficient, right, active case, the Ka, and plot the K distribution. And I'm sorry, and you can determine the Ka, the active pressure coefficient at the depth of Z using this linear curve. So now we can check for the rupture. Here the rupture, the factor of safety criteria is 1.5, and factor of safety against the rupture is computed as allowable tensile force divided by the maximum applied tension. So TA over T max. So let's compute the TA. TA will be N times AS times Fy. So this will be like, if you have a facing element like this, and you have a 4, maybe N will be 4, and then each facing material will have a cross-sectional area, AS, and the Fy will be the allowable stress, or the tensile yield stress carried by the each strip. And then you can also compute the Tmax by using this equation, Kg times sigma V times AP. So then you think about the face material here, and you have a strip, then sigma H times AP will be Tmax, and here sigma H will be sigma V times Kg and AP. So, yep, and we can, the next one is, let's check the factor of safety against the slippage. Here the criteria is factor of safety should be larger than 2.0. And important note is the V2, the surcharge load, is not considered for the slippage check. So the vertical force will be the only the weight of the reinforced block, soil block, and you use the V1 to compute the E and to compute the vertical stress. So then here the vertical stress for the slippage or for the bond will be different from the vertical stress in the rupture. So this will be V1 over L minus 2E. And here the RB will be gamma Z F, the friction coefficient at the depth of Z, times 2B LE times N. Here the LE is the effective length. This is the effective length. Okay. So again, you can have a strip like this, and you have an n number of this, and this is the area, and B, and maybe if this is the failure surface, then from here you have to compute, you have to consider the only take account of this length, LE. And frictional coefficient F is given, right? And gamma Z will be the sigma V, the vertical stress. And here Fg star is interpolated between 1.5 at 0 meter and tangent V1 at 6 meter. So as we saw before, you can compute the friction coefficient F star for depth of interest using this equation. And the Tmax is the maximum applied tension, just like before here, same, right? And when you compute the sigma H, we'll just use the sigma VB for the different vertical stress. Then final equation for the vector of safety is given like this, and you can check for the vector of safety of the internal failure mode of slippage. And last one is just for reference. It's not like widely used. Tie-back analysis is proposed by the Lee et al. In 1972 and 1973, and also it can incorporate the Rankine type analysis and the Coulomb type analysis, and the details are in the you can find the details in the textbook. And in this analysis, the formula for determining failure by slippage is modified to this one, and effective length rather than the L in the original standard method. So it is similar to what we are doing in the revised standard method. Yep, and only the delta, the tangent delta is a little bit different, and the sigma V, how to compute the sigma V will be a little bit different. Okay, that will be all for lecture 20.